Good evening, everyone, and welcome to the Silicon Valley Astronomy Lectures, a program of introductory talks on exciting developments in astronomy, now in its 21st year. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy at Foothill College in Silicon Valley, and this is the 21st year that we've been bringing these lectures, first just to the auditorium at Foothill College, but now over the web to listeners and viewers all over the world. And I want to welcome everyone who's watching us all around the United States and in far-flung corners of the world. These talks are co-sponsored by the Foothill College Science, Tech, Engineering, and Math Division, by the SETI, or Search for Extraterrestrial Intelligence Institute, by the Venerable Astronomical Society of the Pacific, and the University of California Observatories, which includes the Lick Observatory right here in Silicon Valley. And we appreciate the help of all those organizations in making these talks possible. We are in for a special treat tonight as our talk entitled Cosmic Instability: How a Smooth Early Universe Grew into Everyone You Know is going to be given by John Mather, and I'm going to introduce him in just a moment. I want to remind everyone that in this rather complex audiovisual setup that we have, we ask you to ask your questions by emailing our special email address, astronomy@foothill.edu. That's astronomy.foothill.edu. And Dr. Jeff Matthews, the astronomy instructor at Foothill College, is standing by to collect your questions and to ask them at the end of the talk. So without further ado, let me now introduce our speaker. Dr. John Mather is senior astrophysicist and the senior project scientist for the James Webb Space Telescope at NASA's Goddard Space Flight Center. His research centers on infrared astronomy, cosmology, and the development of new instruments for exploring the universe. The James Webb Space Telescope that he's going to tell us about is our next great project of telescopes in space, and the entire astronomical community is really looking forward to that. Dr. Mather was a project scientist and a principal investigator for the Cosmic Background Explorer satellite, with which the leftover radiation from the Big Bang was measured precisely for the first time. For his work, he's received numerous awards, including the Nobel Prize in Physics in 2006 and 3 honorary doctorates. Tonight, as I said, he's going to talk about how the early universe grew into everything and everyone you know. Ladies and gentlemen, it is a privilege for me to introduce to you Dr. John Mather.
Thank you, Andrew. I'm delighted to be here with you, and I do have a story to tell you, which might or might not be true, but I'll give you my best. So I have some beautiful view graphs to show you because I'm an astronomer. That's what we do. So let's see if that will work here. So this is a picture of the great James Webb Telescope that was just mentioned to you. It includes a golden hexagon. It's not really solid gold. This is the telescope that will unfold in outer space beginning in October this year when we plan to launch it. It is a joint project of NASA with European and Canadian space agencies, and of course with a large contingent of engineering and technical talent in Southern California at Northrop Grumman, where that's our big industrial partner right now. I'm pointing out that this is a project available to all human beings. You can write a proposal if you're an astronomer, and we'll read it and can think about whether that's really a great idea. If so, we just might point the telescope at your favorite target. So I will tell you more about that process later, but I want to start closer to the beginning. So, what did I do now? When I was a child, people didn't really have much of a clue about how the universe grew into what we have. Um, it was thought to be so complicated that divine intervention was required. And that was actually not so far from the thinking of physicists, even into the mid 20th century. So, on the other hand, 2,000 years ago, some of the essence of thought had already been done. The atomic theory was recognized as an explanation for how, for instance, a glass of water can evaporate, turning into invisibly small particles. So Lucretius wrote in this poem of more than 2,000 years ago about this. He saw that pieces could grow together, grow into things that you could know and give names to, and then they would disappear. So we have a little bit more quantitative story than that, but it's still the same story that he was telling us so long ago. So here's how we tell it now, more or less. We know of 4 forces of physics, and we know about thermodynamics. So quantum mechanics tells us that everything you were taught about particles actually means that they're a little bit wavy. And everything about a wavy thing that you've learned in school is actually got some particle nature to it. But at any rate, we calculate these properties, basically telling us how do all the pieces fit together. So we've got 92 different kinds of atoms, and we know the chemistry of how they stick together to make molecules. So this is basically the story of all the Lego blocks of the universe. And they're all determined by these mysterious but probably correct stories of quantum mechanics. Physics students have to learn how to make the calculations, but for today, we just need to know that there are Lego blocks of many kinds and that they can fit together. Something we have known for many centuries, of course, is about gravity. Isaac Newton described it very well, and then Einstein improved on it. But basically, it has a feature that hardly anyone appreciates outside astronomy, which is that gravity enables material to spontaneously heat up. In school, you don't learn about how a little block of ice is going to spontaneously boil, but in astronomy, we do that because gravity can pull material back together, releasing gravitational energy and turning it into kinetic energy. So this is a great instability of the early universe continuing to now. So then another thing we've learned, of course, in the last couple of centuries is about thermodynamics. We see that there is a local order. For instance, when you see a crystal of ice, you say, isn't that beautiful? Isn't it beautifully orderly? So how did that happen? Well, of course, when the ice was made, the heat that it had in it went elsewhere, and that increased the disorder of the rest of the universe. So overall, the entropy of the world increased when that happened, but nevertheless, it looks beautiful and orderly to us. In very recent times, we've started to learn about non-equilibrium thermodynamics. And so you and I are all examples of what I call spontaneous heat engines. Nature has found a way to use us to increase the entropy of the world. We eat our food and turn it into whatever we like to do. And that is a way of increasing the rate of combustion of the food to make carbon dioxide. So we are here in order to increase entropy while we do our thing. So part of the story is there. But now let me step back a little bit because we are aware now that there is an expanding universe. I'll show you more about how we come to think this, but the universe is expanding now. It started out smooth and very hot, and it was very unstable. First from various nuclear reactions, particle reactions, and then as gravity acted on the early universe material to turn it into the big structures that we see today. We know the universe is probably infinite. That is to say, it has no boundary. It can keep on going indefinitely far in every direction, at least in your imagination. There's one exception to that. You cannot go infinitely far back in time. The universe does seem to have an age, although you cannot get to the first moment. There is no such thing as a first moment in our story. Now, the last 2 lines on my chart here tell you about the complexity. When I was a little kid, we did not yet know that the DNA in our genes was encrypted in a double helix. And now we know that it's a digital code, that all of our living cells come with decoders for that digital information. So you don't think about it, but your body is actually made up of about 30 trillion digital computers, all reading their codes and doing whatever they need to do, so that you and I can continue to live more or less as we are until those cells decide they're going to stop cooperating. So that's a pretty amazing thing to think about, that each one of those 30 trillion living cells has its own instruction set and its own determination to do what it's supposed to do in its environment. So we've learned about evolution from this story. Now we say, I say, this is not just the survival of the fittest, as people used to say. This is about the survival of the lucky, because there's nothing particularly fit in a changing world. Nevertheless, we are lucky. We are the ones who came down out of the trees and learned how to cook and how to hunt and how to farm and how to build gigantic civilizations of billions of citizens that would have been impossible for the other creatures with whom we share this world. Anyway, another thing that we've come to recognize is something engineers love to do. We build feedback loops and control systems. So each one of those 30 trillion cells in your body has been set up to more or less maintain itself. Biologists call it homeostasis. So it's got feedback loops that replace the dead pieces with new pieces and keeps on going for a good long time. So engineers do this on purpose, and we're still astonished at how many control loops and feedback loops there are inside a single cell, not to say 30 trillion of them operating at once to make you. So pretty amazing story of cosmology and biology all in one little chart. It's not enough detail here for you to test it, but this is a general idea. So we've known for a couple of hundred years how to calculate some instabilities. Euler told us back in 1757 how to do this calculation. When is something going to collapse? If you put a big weight on top of a column, when is it going to collapse as compared to when is it going to buckle? So he figured that out, and it's pretty simple. College students learn this one. It takes a little more calculation for college students to do this problem. If you look at a cloud of gaseous material out there in space, hydrogen atoms and helium and so forth, you can calculate whether gravity is going to be able to pull it together to make a star. And so his searcher, James Jeans, gave us this back more than a century ago in 1902. So we know how to calculate some of these things, but darned if it doesn't get complicated really fast. So here's an example of spontaneous heat engine. You and I are spontaneous heat engines. This is one of personal importance to us. This is the Hurricane Harvey that sat over Texas for some weeks, for just at the very same time that we were testing the instrument package for the James Webb Telescope in the vacuum tank right under that bullseye there. So at any rate, this is an example of how spontaneous complexity can occur given a energy flow. So it's not surprising that we can exist when you take this perspective. But now this is all pretty hard, and I don't know how to do biology. So now I want to work now on the easier parts of astronomy. So stepping back almost a century, Edwin Hubble drew us this graph in 1929. Each of the little dots on this graph is a galaxy. A galaxy represents about 100 billion stars held together by gravity, orbiting around a common center. And what he's showing here is how far away he thought they are and how fast they're going away from us. And so there's a pretty important factor on this chart. Number one is most of them are going away from us with a speed about proportional to distance. And if you divide the distance by the speed, you get the apparent age of the universe. So back in 1929, this is the first evidence we ever had that there was actually an age of the universe. It was about 2 billion years, according to him, because his distance scale was incorrect. But we took a long time to find his mistake. Other thing that's really interesting here is several galaxies in the lower left corner there actually have negative velocities. They are headed in our direction. So in some billions of years, we're going to have a wonderfully exciting collision, except you and I won't be here to witness it personally, but somebody will. So if you believe this story of the expanding universe, then you should be able to figure out what it was like when it was young. So it was calculated in 1948 that it should have been very hot when it was young, and the heat should still exist. It should still fill today's universe, and we should even be able to calculate the temperature. So the calculation then said it should be about 5 degrees Kelvin, 5 degrees above absolute zero, which was impossible to measure in 1948, unless perhaps you'd known there was a Nobel Prize waiting for you if you could. So it wasn't actually discovered until 1965, and then suddenly a huge mad scramble was on for students and professors to go measure this cosmic background radiation. It is very bright at wavelengths of a few millimeters. And so when I was a graduate student in Berkeley in 1970 or so, it was just after this had been discovered, I was looking for a thesis project. So I found Paul Richards and Charles Towns and Mike Werner, and they were all thinking about measuring the cosmic microwave radiation. So I said, I'd like to do that. So I worked with them, and we made a thesis project for me. And to tell the truth, that was it was a bust. The experiment failed to function on the first flight, and I got to write a thesis about a failed experiment. Fortunately, the design was good. It was finished out by my fellow students and advisors, and so it did work the next time. But at any rate, I left Berkeley with a failed experiment under my belt. And I thought, well, I'm never going to do that again. That's too hard. Then I got to NASA job in New York City to become a radio astronomer. And shortly after I got there, NASA said, we'd like proposals for new satellite missions. So this was 1974. It was just 5 years after we had landed on the moon. And NASA's thinking, well, what are we going to do now? Anyway, I said, boss, my thesis project failed. We should do it in outer space. He said, we'll call up our friends and we'll write a proposal. And so we did. And I thought that'll never work, but it's worth trying. But it did work. So 2 years later, I moved here to Goddard Space Flight Center in Greenbelt, Maryland, and we decided to build it. So there it is, an artist's concept in outer space, carrying 3 instruments to look back towards the beginning of time, 2 to measure the cosmic heat, and 1 to look for the light of the first galaxies. So because real engineers made it worked fine, and it was a little scary, but it did work. So within a few weeks, we had our first data. I showed this graph to the American Astronomical Society, and we got a standing ovation for a graph. So why did we get a standing ovation for a graph? It's because it said the Big Bang story, the one we've been telling all these years, is actually about right. All the theoretical predictions and measurements match up as well as you can see on the graph. Later on, we got the error bars down to 50 parts per million. So, okay, this was a pretty tremendous success. There was another thing we were really trying to do, though, which was to look to see, is this cosmic heat equally bright in all directions? And so we measured that too. This was the first time it had ever been measured. And so this is a second instrument on board the observatory. The picture to look at is the one in the lower right-hand corner, which is representing the entire sky with hot and cold spots on it that are very, very faint. The average temperature is about 2.7 degrees, and the variations are about 1 part in 100,000 out of that. So Stephen Hawking looked at this chart and he said, that was the most important scientific discovery of the century, if not of all time. It took a little while for me to understand why that was so important to him and to us, but now I think I can tell you. Number one, those spots represent density variations in the early universe, and we could not exist if they didn't exist. So we are here because of them. The We believe that gravity acting on those denser regions was able to stop the expansion of the material and turn it around to form galaxies and stars and planets, and then people, of course. Second, we figure out from this map that most of those spots come from something called cosmic dark matter, which only astronomers can measure and nobody can see. So it's still a great mystery. And the third point is, if we could ever understand what makes those spots, we would perhaps have the clue for quantum gravity, which is still one of the great mysteries of astronomy and physics. Anyway, so from that, we said many things follow. We should be able to make up a picture of the whole universe. We know the statistical properties of the early universe, and now we can summarize it here. It was very hot and very compressed when it was young. There is no center and no edge. Although people often say, wasn't the universe compressed into a point? No, it wasn't. That was an incorrect story people told you. It has always been, as far as we know, an infinite universe expanding into itself. There's also not a first moment. There is no such thing as the time of zero in our story. And so you can't get there from here. Just as there is no smallest positive number, the time of actually equal to zero is not included in the story. So it's not a big firecracker. There is not a moment of creation. There is nothing before the beginning of the universe that we know about, but of course, we're thinking. So that's the story of the early universe, then how it leads to us. Now I'll tell you a few more details. We need to have a telescope to take pictures to see, because everything is much too complicated to figure out from prediction alone. So the Hubble telescope was launched just a few months after the COBE satellite that did the work I just showed you. And it has taken pictures to tell us the details. We, for instance, learned that not only is the universe expanding, but it's going faster and faster. So a few years back, astronomers believed that gravity would pull all the galaxies together, and they would certainly slow down the expansion. Then we went and looked, and it wasn't true. So these three men got their Nobel Prize in 2011 for discovering that the universe is accelerating, going faster and faster all the time. So huge surprise. Don't believe us when we tell you we know everything. We know everything that we know, and we're happy to be surprised. So now we can make a movie for you of how we think this might have worked. This is an observatory in a computer box. We have colleagues who can run the supercomputers to simulate how gravity could pull material together in the very first moments after the Big Bang. So this movie is called Illustrious, and it represents millions of CPU hours and many, many, many people hours understanding how to make this go. But what they've given us is a simulated box of early material, and they're rotating it in front of our eyes so we can see it. And you can see that it doesn't take very long for it to form into objects, and for them even to be arranged in strings and flat sheets. And this is all the result of gravity operating on random inputs. But who would have known? We only know this because we look, both with our eyes and with computer simulations. By the way, here we're showing explosions happening. So what happens to make an explosion? Well, stars can occasionally use up all the fuel that they have and become unstable. So that's one way that an explosion occurs. Another one is that a black hole can form, and as material falls into the black hole, huge amounts of energy can be released. So both of them have huge effects on the neighborhood, and in fact, such processes would have been happening in our own Milky Way galaxy as well. So up until just about this time in the history of the universe, when the solar system forms, about 9 billion years after the beginning, and about 4.6 billion years ago. So to my way of thinking, this is one of the most beautiful movies there is. The computer folks keep on improving it so that it actually resembles quite well the pictures that we can make with the Hubble telescope. We've even gotten so good at this that we can say, I'm going to study the galaxy over there that was simulated and see if it looks like a real galaxy, and tell you all the details. So is this a hugely important telescope that you don't think of as a telescope, because it lets you see time as well as space. So now I want to show you what we're doing currently to test out this story. Here is the great James Webb Space Telescope. James Webb was our second administrator at NASA, and he was the person who said, John Kennedy, this is how we can get to the moon, and he made it happen. He also said, Mr. Kennedy, we need science. We need scientific laboratories around the country. We need scientific discoveries. We need to send probes through the solar system to Mars, and out of the solar system, we need to put up telescopes. And Mr. Kennedy said, well, we're kind of bankrupting the country, but we'll do it anyway. So anyway, it's certainly an amazing man to recognize by naming an observatory for him. Anyway, here is the summary of the project. There's the great observatory with its 6.5 meter, that is to say 21-foot diameter hexagonal mirror, protected by an enormous sun shield, about as big as a tennis court. Our international partners are listed here, NASA with Europe and Canada, our industrial partner Northrop Grumman in California. The observatory will be operated, by the way, the same way that we do the Hubble telescope. There's an institute in Baltimore, Maryland that does it. So we're sending it up in October is the plan, and we'll show you a little bit more about it. So just to tell you a little bit about how do we decide to do something like this. In 1995, there was a committee formed, and here's Alan Dressler, the chair of the committee, and they wrote a very poetic little book. And they said, okay, we've got what we got from the Hubble. We can see how powerful it is. And you know, the next step is this. Please build us a telescope that's more powerful and can see infrared light. And while you're thinking about that, please also find out how to observe Earth-like planets around other stars. So that's even harder. And we haven't done much of it yet, but we will. So anyway, then he went and met the head of NASA. That's Dan Golden there. And Golden announced to the Astronomical Society that the committee that wrote the report was not nearly ambitious enough. We're going to build a bigger one. And he got a standing ovation. So that's sort of gave us a clue that we had a good shot at building this, despite how hard it turns out to be. So then we wrote some more books. Committees are formed to decide what to do. And these are pictures of the books. And then here on the far right is our expected culmination with a launch of the Ariane rocket in October. Just to give you some sense of the pace of history. You may say, geez, it's taking a long time. From my perspective, it's running as fast as we possibly can to make this happen. Anyway, so what are we going to look at? There are 4 major themes that we use to decide what to build. The one in the upper left says, well, let's look at the first things that happened after the Big Bang, the first galaxies that grew, the process where the first stars lit up and started to rip the hydrogen gas back apart into ions, that is to say protons and electrons. How did the galaxies grow? How do the stars grow? And how do they grow to have planets? And finally, let's see what we can do about those individual planets themselves with a great telescope in space. So I'll show you a little bit about how we're going at this. Number 1, here's the telescope. It's an optical system comprising a combination of 3 mirrors, a big elliptical primary mirror, almost a parabolic mirror, small convex secondary mirror. The light bounces it back into the insides of the works there. And then the sort of most important features of this are that it is cold. It will be cooled down to about 40 Kelvin, 40 degrees above absolute zero, so that it does not emit infrared light to speak of. And it will have to be adjusted to be the right shape when it's cold. We make it out of these 18 pieces of beryllium, and the beryllium is extremely thin. It's about 2 millimeters thick, but nevertheless, it is stiff and it is polished to have the right shape when it is cold. So an astonishing engineering feat that was actually completed just up the road from you in Richmond, California by Tinsley Laboratories. That's where they did the polishing. So we are so proud of that mirror, and it's going to be fine. So then we have a package of instruments. So basically, this is a summary for astronomers of what do we do. We have cameras and spectrometers. Cameras that take pictures and spectrometers that spread out the light of the stars or galaxies into rainbows so that you can tell what's in them and how fast their things are moving. So very powerful general purpose instrument package covering the entire wavelength range from 0.6 micrometers, which you could see with your eye, out to about 28 micrometers, which you certainly could not. So anyway, hugely different science you can do with the different wavelengths. So how sensitive is it? Well, if you were a bumblebee, 1 square centimeter, hovering out there at the distance of the moon from us, we would be able to see you with a time exposure. So it's originally aimed at extremely faint objects, but then we said, well, gosh, the solar system is important too, and there's some very bright things here. Can you do that too? So the answer is yes. Take very short exposures of the moon, sorry, of Mars, and everything on out from there. So we can see it, and we'll certainly be looking. Another picture for astronomers. This is a set of curves showing that the telescope is very much more sensitive than anything else. So I should skip over this, but at any rate, being at the bottom of the chart is good. So very, very sensitive equipment. So what are we going to look at? We will certainly be looking at the first galaxies. This is a piece of the Hubble deep field, a place where astronomers decided to point their telescope for 2 weeks, where there was almost nothing there that they knew about. There's a star in the lower right-hand corner, this little thing with colored spikes sticking out. There's, I think, one other star in this picture that is off the edge of the picture. But at any rate, all the rest of these things are little galaxies, as observed by the Hubble. And Hubble's observatory said, well, we can't see the first galaxies. They're too faint, they're too far away, too far back in time. I need a better telescope. So we'll certainly be doing that project again, much better as far as we can with infrared. We will be looking inside these beautiful clouds. This is an example of a cloud nearby where stars are being born today. What you see on the left is the traditional view of what we call the pillars of creation. It is a very dusty area. Dust prevents us from seeing inside with ordinary visible light, but we know that inside that dusty cloud are new stars being born. And so what would you like to do to see inside? You would like to have infrared capabilities. As we have some infrared with the Hubble telescope, we see that on the right-hand side. But this is analogous to when you go to the airport and they look through your clothes to see if you're doing something you shouldn't do. And they use longer wavelengths of light. They use millimeter wavelengths to see around the fibers in your clothes. So they don't get much detail. Don't be too worried, but they can see around the fibers, just as astronomers can see around the dust grains by using infrared light. Here's an example of how the view of this other nebula changes as you go from visible wavelengths to infrared. It's a dramatic change, and we will certainly be looking for that change with the Webb telescope. Here you see it cycling in colors. We will be looking in the solar system. 2 amazingly exciting targets for next visits by NASA. Europa is a satellite of Jupiter. We know from the Galileo mission, which went there to take pictures many years ago, that Europa is a wet place. It has an ocean covered with ice. There are warm water geysers spitting up something, and we would like to go see what's in those. We would like to see if those geysers have organic material, any sign of life in that ocean. A more ambitious project would be to land on the surface and either melt your way in or drill your way in, or just go to the right place where water is already coming out. So we certainly want to go there. The one on the right is a map of the surface of Titan. Titan is the large satellite of Saturn, and it is unique in the solar system that it has rivers, craters, dunes, weather. Of course, the liquid on that surface is hydrocarbons, methane and ethane, and other hydrocarbons. So, but they have geology. What they use for rocks on Titan is water ice. And this is a fascinating place for many, many things. We are even sending a helicopter to fly around those short distances on the surface of Titan. So if there is, by the way, any possibility that life does not have to be based on liquid water, this is the place you would find it, because we have something so similar to terrestrial conditions, except a colder version, that this is certainly a place to look to see if the kind of life that you are familiar with is the only kind. We will certainly be looking at planets around other stars. Here is our method, or one of our methods. As a planet goes around a star, once in a while, sometimes it lines up and passes in front of the star and blocks some of the starlight. So when it does that, the apparent size of the planet depends on the wavelength of light, because of the various chemicals in the atmosphere of that planet. So some of the starlight goes through the planetary atmosphere on its way to the telescope, and we can tell what's what. So we are already planning to observe about 9 Earth-sized exoplanets, 5 Neptune-sized ones, and 16 Jupiter-sized planets by this method. So we will not plan, or we're not expecting to see signs of oxygen in an Earth-like planet. We don't think we can, but we'll certainly be looking. So this is very exciting planetary explorations coming with us. Now, just to wrap up, I want to show you a little bit about how do we get there? How do we get the observatory up into space? So we started by putting the telescope itself together in the clean room here at Goddard Space Flight Center in Maryland. And there it is, the golden hexagon, which was absolutely beautiful to look at. And then we decided we better find out if it can survive launch. We put it in a clean tent, and we put it on top of a shaking device, which can apply about 50,000 pounds of vibration force to this very delicate telescope. And we decided, okay, it survives. We will go on and put it into the next step. So to get there, we put it in its giant mailbox and drove it around the highway to Andrews Air Force Base here in Maryland, and the entire truck and shipping container went into the airplane. And then they flew it down to our Houston base, Johnson Space Center, took it out again, put it in the vacuum tank there. It was called Chamber A, which was used by the Apollo astronauts to rehearse getting out of their lunar capsule and walking down the ladder onto the surface of the moon. So a very historic spot. Next, wrong direction here. Then we put it back in the airplane, sent it to California, where it is now. It has been attached to this piece, which is the warm piece of the observatory. And we have just sent it through its last vibration test, and it is unfolded now. We are in the process of folding it back up so that it will go into the next shipping container. And here is a picture of this one. It's a special ocean-going barge, which will take it through the Panama Canal on its way to the launch site in French Guiana. And we're going there because the European Space Agency is buying the rocket. And it's a good place to launch from, and it's a good rocket. Then in October, we push the button, and this happens. It goes up into space. And then we very carefully unfold it by remote control in outer space. So that'll be a scary time. We have, however, done everything we should to make sure that it'll work. Here is just one last beautiful picture of the observatory in clean rooms. While it's partially unfolded. We are sending it out to a place called Lagrange Point 2. It's 1.5 million miles, 1.5 million kilometers, 1 million miles from Earth in the opposite direction from the sun. So it'll be overhead at midnight here. And it's a great place to put a telescope because it doesn't get any farther away. It stays with us all year long, and we can communicate with it very well. It's also the only place in the solar system where the sun, the Earth, and the moon are all appear to be in a straight line. So you can put up a one-sided umbrella and protect yourself from the heat. So here is our scary movie. You know, it took 7 minutes of terror to land on Mars. This is different. This takes a couple of weeks. And unlike the Mars landing, this does not have to be done all at once. We have the opportunity and the plan to take each step, make sure that it works, try again if it doesn't work exactly right, because we have 2 ways to accomplish everything. Every motor has 2 sets of electrical windings and 2 controllers, for instance. It's an extraordinarily complicated creature. And you'd say, are you sure you have to have it that complicated? And the answer seems to be yes. We tried very hard to find an alternative that was simpler. And the answer was, well, if you make it smaller and simpler, it won't do the job. So let's go on and do this. We just know that it's really hard. So it takes about 2 weeks to go through this process that I'm showing you here of unfolding everything and getting it into about the right place. Then it takes another total of 6 months to get everything completely focused up, tested, and ready for doing science. So if we launch on October 31st, then we should be ready to show you beautiful pictures at the end of April in 2022. So of course, this is a picture no human can ever see because in space, the telescope will be in the dark. So now I want to move on to what's next, because of course, building the Webb telescope is not the only thing astronomers want to do. We have other great ambitions. Now, it's pretty hard to put a telescope into space, so let's see what we can do on the ground. So here are 3 gigantic telescopes under construction on the ground. The biggest one is the European one. It's the 39-meter telescope. It's being built in South America. It's about 6 times as large as the Webb telescope, but it's stuck here on Earth. So that's good because you can get to it to make it work better. It's bad because air is turbulent and it blocks the infrared light, especially that you would like to see. Nevertheless, it's worth trying. So we will be using this amazing technology called adaptive optics. Back in 1953, it was conceived, but nobody could actually do it then. Now we do it on purpose, and it was developed by military technology and then redeveloped by astronomers. Now it's not secret anymore. So the concept is point the telescope at a star, make sure that you can adjust the mirrors of the telescope so you get a sharp image of that star, and the whole area around the star will also be a sharp image. So we can compensate for the turbulent atmosphere of the Earth and get sharp pictures this way, even with that gigantic telescope. So a tremendously startling spin-off of the Webb telescope technology is the picture on the right. The person who figured out how to polish those wonderful mirrors for the Webb telescope said, well, I could figure out how to do this picture on the right as well. I will work out the math. I will show you how to make the parts. And now when you go to your eye doctor, you can get the same kind of adaptive optics concept to look into the back of your eye. And if you're a San Francisco or Oakland football player, you will say, I need to see better. Can you make me see better? And the answer is yes, they can use this system to correct your natural lens in your eye and get 20/10 vision. So if you want to know how they're so good at seeing things so far away, they can help. So, so this is possible. And so let's say, well, How are you going to do it? Well, we have many ways, but this is an idea that I'm working on currently that I thought you might be interested in. We can put a laser guide star in space to focus the telescope on, and we can put it wherever we need it, at least for a while. So working on this idea, and you never know whether we'll get chosen to do it, but I think it could happen. And if we could do that, then we could get really sharp pictures. And then the next step after that is, let's put up a star shade. It's about 100 meters across in the same kind of orbit. Cast a shadow of a distant star right onto the biggest telescope we can get. And if you could do that, you could get this picture on the right-hand side. You could get Earth, Venus, and Mars in a 1-minute exposure. So it's not impossible. It's pretty hard, just not impossible. So if you want to know, are there little planets out there with life like we have on Earth? This is one of the ways to try. It's not the only way, it's one of many. But the others will basically all require putting another even bigger and better telescope in space. So if you could do this, then we'll be able to get a spectrum. A spectrum like this shows the molecules of the atmosphere of another planet. And the one I am so thrilled about here is that the blue curve is what we think we would see if we could look at another Earth way out there. We would see these little ripples that are labeled with oxygen and water and oxygen and water and water. And we would be able to say, yes, there's a planet out there that is a lot like Earth. It has oxygen. So it might be possible. It'll take us quite a while to do this. This is a hard project. But anyway, I think I should come back to the original questions and say, well, how far could we go? Can you go to the stars? And the answer seems to be no. The answer to Fermi's paradox about where are the neighbors is it's too far. That's my opinion. But when we finally do develop the wonderful products of Silicon Valley into super intelligent robots, then we can say, well, robot, do you want to go? We'll help you. Or maybe not. Maybe let's say they want to go. Maybe they say, anyway, who knows what the distant future calls to do. But even in 1 billion years from now, the nearest stars are still going to be pretty far away. So let me wrap up. I'll be very happy to have your questions. And I don't think I answered them all yet. So thanks for coming, and thanks for thinking with us about how this all might work.
Thank you so much, Dr. Mather. Let's stop sharing the slides.
Okay, there we go.
There we go, great. And let me thank you for what in another context was called the greatest story ever told, the story of how we got here and what we're capable of doing once we evolved. Very exciting developments, and we wish you the very best of luck with the launch of the web and the unfolding of the web. We're all going to be keeping our fingers and toes crossed as the latter part of the year comes. But thank you again for that talk. And we want to just mention that the next talk in the Silicon Valley Astronomy Lecture Series is going to be March 10th at 7 p.m. when Dr. Eleanor Gates of the Lick Observatory is going to talk about Lick Observatory during pandemic times and compare what it was like in the 1918 pandemic for a major observatory and what it was like last year. So please join us March 10th at 7 p.m. But now I want to turn things over to your questions. I'll remind you that if you want to ask a question of Dr. Mather, we are taking those questions at astronomy@foothill.edu. Email those questions to the address astronomy@foothill.edu. What I'm going to do now is to turn things over to the astronomy professor at Foothill College, Dr. Jeff Matthews, who's going to be sharing your questions.
So, thank you, Andy, and thank you again, Dr. Mather, for coming out and speaking with us this evening. I'm going to dive right into the questions that people have sent, and I'm going to say up front, we've received a ton of questions. I've tried to sort of group them. I've tried to identify questions that are very similar to try to hit as many of these as we can. There we go. So we've got a question from Marina asking, since Webb planning started in 1995 and is only launching now 25 years later, what space-based missions are being planned for 25 years from now?
Oh, goodness. Well, 25 years from now is a long time, and we haven't made up our minds. What astronomers do is every 10 years, we have a giant committee meeting, and we write a book about what we wish for and what we think the most exciting things could be. And this time, we have been considering 4 gigantic telescopes, 2 of them specially aimed at exoplanets and the search for planets like Earth way out there. One of them is more powerful than the other. One of them aimed at far infrared light. That's quite a different technology. One of them looking at X-rays to see black holes and neutron stars and other astonishing, very hot things. So the committee might tell us we need them all. If I were the committee, I would say we need them all. And that tells us we have probably 20, 30, 40, 50 years of great telescopes in front of us before we run out of great ideas, and then there will be new ideas.
All right, so thank you for that. And now we have a question from Chelsea asking, why is the mirror made in 18 pieces and why is it beryllium?
It's made in 18 pieces because we can't lift a big piece. The telescope is bigger than the rocket. So we have to fold up the telescope. So we have to find some way, and hexagons are actually a pretty good way to make a big piece out of little pieces. They are made of beryllium because it's extremely lightweight and very stiff, and especially, this is the most important part, it keeps its shape. You can cool it down and warm it up, cool it down, it'll come back to the same shape that it was. So when you say, I've built it right, it'll stay built.
Okay, and then we have a related question from Phil asking about those ground-based telescopes. Why are ground-based telescope mirrors so much thicker and heavier than the JWST mirror?
It's easier. We had to expend an immense amount of effort to make the Webb telescope mirrors thin, and they need to be thin because the rocket has to lift them into space. So the Webb telescope mass is about half that of the Hubble telescope, even though we have about 7 times the collecting area. So we can't get a much bigger rocket, so we just have to make something lighter weight.
Okay, and one more question, sort of lumping together several people asked something along these lines. So Elena asked, how long will Webb be operational? Oh,
I didn't tell you. We have fuel on board for about 10 years of operation. If we're lucky with the original launch and the hardware, it could run a lot longer.
Okay, and so then we've got going into some questions about the science that you discussed in the talk. So we've got a question from Douglas wondering, can the expansion rate of the universe vary from place to place?
We haven't seen any evidence of that yet, but we do have to test it. So for instance, you should see, is it the same rate in all directions? And here locally is the local expansion rate in the nearby neighborhood, just the nearest, say, a few 100 million light years. Is that the same as it is farther away? So we have done some tests. We haven't seen any sign that it's not the same, but it's not something you can assume. You have to test.
Okay, and sort of there's several of these sort of cosmology related questions. So I'll try to sort of lump these all together. From Maria, we have early in the talk, you said there was no t=0 and no special beginning moment of the universe. And how does that relate to what we call the Big Bang?
Okay, the way I think about the Big Bang is we can run the expanded universe backwards in our minds. Okay, it's expanding now, let all the pieces run back together. They collide with each other, they get hotter and hotter, the atoms are ripped apart, the temperature goes up, the density goes up, and finally we say, I have no idea how to calculate what happens after that, or maybe I should say before that. So at the most extreme conditions you can imagine, we don't know what to say. So then I say, well, let's call that the Big Bang. So it's the expanding infinite universe in its most extreme early conditions that we can imagine.
Okay, and then one more cosmology question. Sort of several people asked about the video that you played where you showed the cosmic web showing strand-like structures rather than like globular spherical things. And so why is that?
Ah, okay. Well, that's actually the sort of unexpected result of gravity operating on random initial conditions. On the other hand, if you wait long enough, these parts do tend to pull together. So our own galaxy will be colliding with the Andromeda Nebula in a couple of billion years. So what starts out as long, stringy things will end up a lot rounder in the future, given time.
Okay, so then you've answered a lot of questions for our audience. I think we'll make this the second to last question here. Try to start tying this up. So there was a question, somebody was asking, if we use the James Webb Telescope along with, say, gravitational lensing, maybe using our sun or maybe a planet in our solar system or something, would we be able to see greater details, maybe even surface features of distant planets?
Oh, we can't do it with the Webb because it's not in the right place. But other people have worked this mathematics out. If you go really very far away from the sun, I don't remember how far, but it's many, many thousands of times farther away from the sun than we are. And you sit there and you get yourself perfectly lined up. The gravity of the sun can magnify a distant object and get immense magnification. So people have worked it out. I don't think we can do it anytime soon, but at least we know what you would have to do.
Oh, okay. And so then going into our final question for the evening, Karina was asking, with what you were showing about looking at planets, why will these studies be looking at the planet in different sizes and different wavelengths instead of just doing the spectroscopy like you showed us at the end of the talk?
Well, it is actually equivalent. The planet looks bigger at some wavelengths than at others because the molecules are more absorptive at some wavelengths than others. So it's really equivalent. It's just a different way of saying the same story.
Right. Well, I'm going to jump in here and use the moderator's privilege to ask one or two more questions.
Okay.
I would love to hear what you're most looking forward to. What project with the Webb telescope are you most looking forward to?
Okay.
You
Well,
it's like asking what child do you like the best? I know.
I'm hoping that we get a big surprise, something that nobody has thought of to look for, but it turns up. So I can guess where we might get a surprise. Everything we know about planets has been a surprise. So I think that could continue. I just don't know. That would be great. The other thing I'm guessing about is things in the very early universe where I can imagine maybe, I'm not a good imaginer, but something happened early on. And all of the pieces that we're interested in were swallowed up and disappeared. So there are none of them left to find now. Now, most kinds of things you say, well, they didn't all get eaten up, so some of them are still left from the early times. But we're beginning to get some signs that something's fishy about the very earliest times. There's a measurement that says the cosmic optical background. The universe is about twice as bright as you can explain with all of the pieces that you can find. So are there more pieces? Maybe. So I'm kind of hoping there's something surprising in that territory.
That sounds wonderful. And finally, let me ask what my students always want to know is who decides who will be in charge of deciding, out of all the exciting projects that the Webb could do, in what order they'll be done, which one will be done first. Describe for lay people who don't know how that process works, how
Okay.
those decisions will be made.
Okay, well, the way we do it was every now and then, we announce there's a chance to write a proposal. So we say, everybody out there from Azerbaijan to Zanzibar, you can send us a proposal and we'll think about it. And so we form up committees and to read them. So we got, I think, 1,173 proposals. It's an immense number of proposals, and about half of all astronomers worked on the proposals. So that means you got to find a committee that's fair. So that's actually pretty tricky to find committee members who are not competing against the proposals that they're reading. But anyway, we set up this process. We get a couple of hundred astronomers to read the proposals, and then they vote. And they say, well, this is what we think. And then they send their letter to the director of the Space Telescope Institute, and they try to persuade that person that this is the right choice. And usually they'll say yes, and sometimes they say no. And then even that's not quite enough, because we say, well, what if somebody says something about to happen next week? I need their telescope now. And so we have that process available also.
So like director's discretionary time?
Yes, director's discretionary fund. Say a comet's about to hit Jupiter, as happened with the Hubble telescope. Okay, let's figure out how to do that.
Well,
so, yeah.
This sounds very exciting. And I know that one of the most exciting things will be, as you said, that we don't know yet all the things we're going to discover. So let me, on behalf of all of us, thank you, not just for this talk, but for all your wonderful work on this telescope. And we wish all the best for the telescope and for all the observing that's going to go with it. Thank you, Dr. Mather, for a wonderful presentation.
Well, thank you, Andrew. And I need to pass on the thanks to the thousands of people who are actually working on the observatory to make it happen.
Great. So thank you all for joining us. This has been a presentation of the Silicon Valley Astronomy Lectures, a regular program bringing you the latest developments in astronomy. We encourage you to join us again on March 10th, when we're going to be back with another exciting lecture. And that concludes our evening.